In this video, I want to look at some of the properties of dot products. First, I want to look at the special case that u is equal to v. So instead of doing u dot v, I'm going to do v dot v. In this case, I would multiply things in the corresponding position, so v1 times v1, or v1 squared, v2 times v2, or v2 squared, etc., up through vn. Well, this is the same thing as the length of v squared. So we do have a property that says the length of v, or the norm of v, is the square root of v dot v. In addition, dot products have many of the same algebraic properties as real numbers. Let's let u, v, w be vectors in Rn and k be a scalar. My first property, u dot v is equal to v dot u. I can switch the order of these. Next, u dot v plus w is equal to u dot v plus u dot w, so it does have the distributive property. The next one, k times u dot v is equal to ku dot v, or u dot kv. In other words, I can take the dot product and then multiply by a scalar, or I can multiply one of the vectors by the scalar and then take the dot product. Finally, v dot v is greater than or equal to 0, and it's only equal to 0 whenever v is equal to 0. So it is always positive, except the one case where we start with the 0 vector, in which case it's equal to 0. My next property, if I dot the 0 vector with any vector v, I will get 0. Just like I have the standard distributive property, I have the right distributive property too. I can do u plus v dot w and get u dot w plus v dot w. I can also distribute over subtraction. U dot v minus w is equal to u dot v minus u dot w. Similarly, I can distribute on the right with subtraction. U minus v dot w is u dot w minus v dot w. And so let's look at some examples of how we might be able to use this. Let's suppose we want to simplify u minus 2v dot 3u plus 4v. So I can use my distributive properties to say that this is u dot my second parenthesis, 3u plus 4v, minus 2v dot my second parenthesis, 3u plus 4v. So I went through and used my distributive property where I distributed the second parenthesis through the first. Using the distributive property again, this will be 3 times u dot u plus 4 times u dot v minus 6 u dot v minus 8 v dot v. If I simplify this, this is 3 times the norm of u squared minus 2 times u dot v minus 8 times the norm of v squared. Next, I want to look at the Cauchy-Schwartz inequality. So the Cauchy-Schwartz inequality looks at two vectors, u and v. And it says the absolute value of the dot product u dot v is less than or equal to the length of u times the length of v. And I will not prove this directly, but this is a very important property whenever we're talking about dot products. Another very important property whenever we're talking about dot products is the triangle inequality. The triangle inequality says that the norm of u plus v is less than or equal to the norm of u plus the norm of v. So I actually want to show this one's true. And usually when we're dealing with norms, it's easier to deal with the squared. So I'm actually going to start with the norm of u plus v squared. By definition, this is u plus v dot u plus v. We can use our distributive property to get that this is u dot u plus 2u dot v plus v dot v. I'm going to rewrite this as the norm of u squared plus 2u dot v plus the norm of v squared. We know that this is less than or equal to the norm of u squared plus 2 times the absolute value of u dot v plus the norm of v squared. And this has to be smaller because if u dot v is positive, these are equal. And if u dot v is negative, making it positive would make this sum larger. We can then use Cauchy-Schwartz to say that this is the norm of u squared plus 2 norm of u times the norm of v plus the norm of v squared. So our Cauchy-Schwartz inequality did give us this inequality here. And then we can factor to be the norm of u plus the norm of v squared. And taking the square root of both sides gives me this triangle inequality.